My name is Tomasz Limisiewicz. I'm a PhD student at Charles University in Prague. And main focus of my studies is interpreting the neural networks for language processing. So I have maybe some more remarks about my university and my studies at the end of the presentation. So if I have more time, I have any time left, then I'll go back to some introduction of some other members of our group and our university, our institute, for those who may be curious about that. So I'll start with presentation. I plan to make a few breaks during presentations for questions. And also I'll take questions after the whole presentation. So is it okay, this way of presenting? I don't hear.
It's okay. It's okay.
Okay, great. So let me start by providing some definition what we work in interpretability. So there's actually many definitions from interpretability. It's not well-defined task in machine learning and especially in NLP. I like the definition which says that the interpretability is the degree to which human can understand the cause of the decisions of a model. I would also add, especially in language processing, that also the function of the model, how this model reaches this decision, which information it uses, which is quite important for many tasks in NLP. We mostly deal with black boxes. So black boxes are the systems that which do not reveal their internal mechanisms. So we need to use some additional methods, not only define the system, but after having the systems which performs well on some language processing task, then our aim is to grasp, to understand how it reaches its decision, its accuracy on the task. So in recent years, NLP tasks were mainly solved by deep neural networks. They achieved state-of-the-art status. At the last conferences, the most papers are on deep neural networks, which are trained for some tasks or which are used for transferring knowledge to other tasks, and it's now the main focus of NLP research, I would say. So those models usually just learn the patterns which are presented in large language corpora, are not provided any explicit linguistic knowledge. So those are not expert knowledge, where we can expect them to get some informations from annotators, from linguists. They get them only through looking and training to annotated corpora. And therefore, the large neural models are black boxes, and we don't really know that much about how they function, what's happening in their internal states. So, for example, here we have an example of a model that which has English text in the output, and because I'm in Prague, it outputs Czech sentence, saying it is a black box, and we see that input is fine. We can guess that output is also fine, but we don't really know how the how it's processed inside this black box. So my focus is to open this black box and look inside to answer the questions like how the model works, whether it's really have some grasp of abstractions, whether it's like learned from data, because we don't expect it to have the same abstractions as theoretical linguists have, but we sometimes observe that the model has its kind of representation, way of representing the language, which can be it's a bit artificial, but specific abstraction of the language learned by the model. So we can say, maybe it's an overstatement, that somehow we can examine how this model understands language. And I think very important point for motivation for this work is the opportunity to improve the neural models. If we can identify the premise or the causes of the decisions of the model, we can see whether those decisions are based really on the language as it's in the input, whether it's like on factual information that we provide to the model, or there's some spurious correlations that doesn't exist in the language, but based on the data, the model can connect some points in the way that leads to correct output, but it's not really the way we as humans would connect those points. I will talk about this problem later. So now we can just think that there can be some spurious correlations which can exist in the data and which can be used by the model. And we don't really don't want the model to use those kind of inference. I prepared some examples. Here we see that we can, for instance, probe or check the model, how it works on question answering. And we can identify the parts of the sentence which are important of making particular prediction, and also try to change the sentence or change the paragraph to hint the model to make another prediction. This is called minimal constructive editing. It was also the work at last MLP from University of Washington. When I talked about the spurious correlations, I think the currently very popular topic is gender bias in the models. When, for instance, in machine translation, we translate sentence as shown here, the doctor asked the nurse to help her in the procedure. And based on this sentence in the English, because we add a personal pronoun with female gender, we can expect that the doctor should be translated as female. But then usually in the training data, we see that because in the population of, in the number of doctors in workforce in English-speaking countries, usually doctors tend to be male. And this translation system can wrongly assume that every doctor is male, and then in translation, translated it to male form, which is marked in Spanish. Also, a bit funny example was I found when I invited my friends over Facebook for this meeting. I used some emojis and used Polish text. So the Facebook translated this text, and from unknown to me reasons, it translated the robot emoji into word handsome. So yeah, some colleagues of mine suggested that maybe it's because of some emotional state of the system, but until we check the causes of those translations, we can't really know. So the plan for this presentation is I'm starting now with this part when I mostly talk about motivations for interpretability. Then I will mostly talk about one specific method of interpreting neural nets, which is probing. Then I go forward to our addition to probing, which is orthogonal probing. That's the method which can identify the specific parts of the embeddings that encode specific linguistic information. I will talk a bit about limitation and possible applications of those methods for controlling biases in applications for improving the neural nets. So just a quick note on terminology, the words I will use, because when I think about interpretability, I mostly focus also on some subfield of this growing field. And when I talk about neural network, I will have in mind mostly transform-based models, which are currently, I think, most popular for transferring knowledge, for instance, from large language models, especially from BERT, which gained popularity a few years ago, but it's still widely used as the source of language representation. So sometimes interpretability is also called by some people as BERTology. So it's really study of BERT internal representations. But I think it's many cases we also go beyond BERT, but also most work I will present of later will be about BERT, so we'll be in this field of BERTology. I will talk sometimes about embeddings, and when I say embeddings, I think the vector representation of the model, but it's not necessarily the output representations after last layer. I also consider those hidden states between particular layers in BERT. So those I also will call embeddings. And then representations. So when I say representations, I mostly have in mind all numerical representations of data in the model. So in transformer, those will be those embeddings, and also in some cases attention weights inside those multi-head attention layers. There are very many interpretability approaches. I list just a few here. There are much more of them, but today I will mostly talk about one specific approach, which is probing. So let's go into the probes. The probes, I think, have been used for interpreting neural models for about 4 or 3 years mostly. So just after the first large language models, first language model as ELMO was proposed, and then people wanted to see what ELMO encodes and what information we can expect from it. Then BERT was proposed, of course, and most research focused on BERT and subsequent models which are based on transformers, so Roberta, BART, and many others. So in probing, we text those representations of contextual neural networks, and freeze the parameters of the network, so we don't fine-tune. This is a big difference from fine-tuning. because we want to see what is already encoded in those representations. Then we add some simple layer, so simple neural layer usually on top of those representations, and want to learn some downstream tasks. For instance, take the representation of bird and then add a simple one layer classifier on top of that, and want to predict part of speech tags. And we assume that the accuracy of the probing classifier can somehow approximate the extent to which the model captures this particular language abstraction. For instance, here we often say that bird understands morphology because we can probe it for part of speech tags. It's a bit of an overstatement. I will talk about it later. Also, more recently, there were a few works on probing for syntax structures. Here I just present shortly two most popular syntactic structure. One is dependency structures. I think this is based on universal dependency, and the other is constituency tree. And we can train the probes to see whether, in this case, syntax is encoded in the underlying model. There were a few approaches. One was edge probing, where we provided two representations of two tokens into the probe, into classifier, which was just linear classifier, and answered the question whether there is an dependency edge between those two tokens. More recently, Hewitt and Manning proposed a structure probe. I'll talk more about it because this is also the beginning points of my works. And in structure probing, we can take two vectors, so two embeddings, and then learn this projection. So here we, instead of classifying, we approximate. And what we approximate the distance between the tokens, between the words in a dependency tree. And the distance is defined by just number of edges between those two words. And therefore, by Euclidean distance of these projected embeddings, we want to approximate the distance of in dependency tree. And actually, this approach was quite successful. It got more than 80% UAS on Penn Tree Bank. So I just remind that there is no fine tuning of BERT. This is just frozen layers of BERT in this case, and just adding just this linear transformation, which approximates the distance in a dependency tree. So here are visualizations of those three approaches I mentioned. So first, there is part of speech probing. So just we take BERT, then we apply probe for classification. The edge probing, we take pair of words, feed it into probe, and get the information about the dependency edge between those words. In structure probing, we can first define our gold matrix, which is just those distances between words in dependency tree. So here, for darker colors represent smaller distances, and we optimize the probe to approximate those distances. So in the right corner below, we see those approximation made by structure probe. Interesting question we can ask with probes is which specific information is encoded where in the model. In the work of Tini et al., who mostly worked with those classification probes, they probed for different language tasks like part of speech tagging, semantic parsing, and others, and found out that specific layers of BERT specialize in specific language information, starting from morphology in the lower layers, then syntax, semantics, and coreferences. So they noted that this order is similar to the order of processing the language in standard NLP pipeline. When standard means pre end-to-end pre deep neural networks. So we observed that for syntax, we can mostly get good accuracy of probing when we probe it from upper mid layers of BERT. So for BERT base, it would be about 8. For BERT large, it would be 16. So BERT base has 12 layers, BERT large has 24. Interestingly, when we probed for syntax in machine translation, from the encoder of machine translation, we observed that the higher results were on the upper layers. And we think it's because in machine translation, there is still another part of the model, which is decoder. So this syntax information tends to appear more in last encoded layers to be used than by decoder. So here I want to make a short pause for whether to take some questions. Are there any to the introduction and the background on interpretability? I think I don't see chat. So please unmute, or if there is something in the chat, someone can.
There's nothing in the chat window. If there are no questions, we can continue.
Mm-hmm. Sure. So I will continue. So now we talk about our work, which is orthogonal probe. So in orthogonal probing, we base on the method proposed by Hewitt and Manning, I shortly mentioned before. We also probe for syntactic dependency, but also want to probe for other linguistic information, like lexical hypernymy. And we also probe for non-linguistic structures, which I'll introduce in a few slides. We showed that this method is capable of decomposing embeddings into parts which encode specific linguistic structures. So just again, a few words about structure probe. So I already said that those probes are capable of approximating the distance in a dependency trees. The alternative of this probing task is depth in a tree. In depth in a tree, we just approximate, you can say, distance of the word between word and the root of the tree. So how depth in this dependency tree this word is, and we do it instead of measuring Euclidean distance. We take a norm of the projected embedding, and if you probe for both depth and distance, we can recreate the actual directed dependency tree. So in our work, we continue with dependency trees. The example is visible here. We add also another source of linguistic information, which we call lexical information. And it comes from hypernymy hierarchies, which we take from WordNet. So in WordNet, we have two big trees or two hierarchies of nouns and verbs. And similarly to the idea in dependency tree, we can calculate the distance between particular words, particular word senses in this hierarchy, and define the distance, which is a number of edges in this hierarchy. We also introduced two baseline structure. One is position in the tree, which is not very interesting. It's just right branching tree. So we order the sentence from left to right. So in this example, there would be artificial root, and we go word after word to the dot. And we also generate random trees. So we just generate some random structures. We do it to check whether those structure probes will memorize the data we provide them during probe optimization. The mathematical equation of structure probes is straightforward. We take embeddings of this frozen model and multiply them by a trainable, tunable matrix, which is linear transformation, to get the projections, which has this property that the Euclidean distances between those projections will approximate distances in dependency tree. We make a slight modification. So we decompose this linear transformation to two parts. One is orthogonal transformation, which first rotates those embeddings, but didn't scale any of the dimensions. Then we use element-wise product to multiply the projection by also tunable scaling vector. So with SVD, those two equations are actually equivalent, and we can express any of the linear transformation by orthogonal transformation followed by scaling vector if we are only interested in the distances between projections. However, the training of the probes is a bit different. So we use gradient optimizations when the differences between those two approaches emerge. And our motivations for this formulation is that with scaling vector, we can interpret each of the dimension in scaling vector, each of its element, as importance of these dimensions for the probe task. So when we see that there is element in scaling vector which has high absolute value, we think that these dimensions will be important for instance, dependency parsing. Also, with this formulation, we can probe for two tasks jointly. So we can share orthogonal transformation and use two scaling vectors, which are responsible of getting projections for two different downstream tasks. For instance, here could be dependency and lexical information. We observed that after training, those values scaling vector tend to converge to zero. There are only sparsely distributed elements of the vectors which were far from zeros, and therefore we could see how large subspace of the embedding space encode each each type of the information we probe for. Moreover, when we probe for two information jointly, then we can compare the overlapping dimensions which were used for each of those informations. And we observed that in probing for lexical and dependency information, we observed that those two vectors focuses at disjoint sets of dimensions. So here on this histogram, we plotted in each bin, we plotted 10 dimensions, and the height of the bar represents how many of those dimensions were kind of selected by the scaling vector for one specific task. And we see that for syntactic tasks and for lexical tasks, those dimensions are disjoint. So therefore, we can identify the disjoint orthogonal subspaces of the embedding space, which encode each type of the information. So the results I just showed are from 16 layers of BERT. We observed this separation in most layers from the first, when it was less pronounced, through 6, 16, and all between, and it disappeared only for the last layer. We think that it's because in the last layer, the representations are more responsible to encode the information, the mixed information, which is needed for masked language prediction in BERT. For other sources of information, we also observed that this entagon appears in for lexical and positional task. Here are just the same results, but shown in the numbers. And this matrix confirms that there are no joint overlapping dimensions between lexical dependency probes, and there are only a few which are shared between lexical and positional probes. Moreover, we see that those subspaces identified by orthogonal probes are rather of low rank, varying from 14 for positional depth up to almost 300. But this is the number for randomly generated trees, and we think that for randomly generated trees, because they are not really encoded in the representation, the probe are very capacity greedy. So if they want to memorize some kind of information, then take as many parameters, as many dimensions as they can. So those are the outcomes of this work, that we first introduced new structural objectives. We showed that the probes are capable, this formulation is capable of identifying sufficient rank for each of the tasks. And we showed that lexical and dependency structures, based on our results, are encoded in orthogonal subspaces. So here also I make a short break for questions. I hope it was clear when I presented our orthogonal probes. So if there are any questions about our terminology or our formulation, our methods, then please ask.
No questions so far, so you can continue.
Okay.
Maybe there will be some at the end.
At the end, okay. Because I'm just afraid that if someone doesn't understand like this work, then on the next work I will also base on this information. So I hope everything was clear, or maybe I just lost everyone. So anyway, I'm going forward. So in our next work, so this is also a bit reason why I'm here, because it was the work on MNLP. We use this orthogonal probes to analyze multilingual representations in embedded. So we focus on 9 diverse languages, and our motivation was to see how similar are the representations of those linguistic information across languages. We base our motivation of the question, which was also asked by Vulic et al., who pondered to what extent the cross-lingual embeddings are similar. They similarly code linguistic phenomena across languages. We asked 2 questions: whether language signals are encoded uniformly across languages. So if we can find syntactic representations in the embedding, whether we can transfer this to other language. So we could find the syntactic information for English in multilingual BERT in the same place, for instance, as for German or for Chinese. And if that's not the case, we wanted to ask whether there is some sort of orthogonal mapping which can bring 2 embeddings distributions together, and then after some rotation, maybe we could then identify some subspace which encodes, for instance, syntactic dependency across languages. It's also important to note that before, Xie et al. Also used structural probes to probe across languages, and in their work they had very interesting visualizations of manifestations of different syntactic dependencies across languages. So in our work, we focus on, again, on 2 linguistic signals, which are syntactic dependencies, which we have from universal dependencies. And we also use multilingual word nets. So it's word nets for many languages where maybe I said multilingual, but we use word nets for different languages. So just like multiple monolingual word nets to probe for lexical hypernymy. And then we use our orthogonal probes. And in first setting, we don't make any assumption about the similarity between the distributions of the embeddings. And we just train the separate instances of probes for each language. We use this orthogonal probe, but for each language, we probe separately. We want to identify the highest results we can get for each language in those tasks. Then we make the isomorphicity assumption. So in this assumption, we think that those linguistic signals are encoded in different languages, but not uniformly, not in the same subspace. But we think that maybe there is some sort of orthogonal transformation that can map those representations together, so map the subspaces together, and then after this mapping, then we can identify this shared subspace which encodes specific linguistic phenomena. So we model this approach, model this assumption by probing with shared scaling vector for a task. So we have one scaling vector for each task, but we train separate orthogonal transformations for each of the languages. So with multiple orthogonal transformation, each transformation rotates the space. So therefore, we learn this orthogonal mapping, which maps the languages across, which maps the representations across languages. And the last, the strongest assumption is the assumption that the linguistic information is uniformly encoded across languages. So here we share both scaling vector and orthogonal transformation across languages. So we just take one probe and apply it for all the languages together. So this is truly multilingual probe in this case. I don't have much time, so I will just talk about the main findings of this work. Is that we compared those approaches, the second and third, to the first one, and see whether adding some more constraints, so constraining the probe more with these assumptions, whether we can achieve comparable performance. So when we use just train separate orthogonal transformations for all the languages, we obtained orthogonal transformation or comparable performance. However, when we wanted to, when we shared all parts of the probes, the performance dropped, but it was mostly observed on typologically different languages. So the languages which had different typological features than English. I will skip those tables during the paper. Also, I have I can, after the presentation, I can link to my talk from MNLP when I talk more about this specific paper. So maybe just I will reiterate the finding that syntactic and lexical information is uniformly encoded across multilingual BERT representations for languages similar to English. So we define the similarity based on the typological features that we took from walls. And for other languages, the orthogonal mapping could improve the results of probing. So we could find this orthogonal mapping and bring those subspaces together. That's the meaning of this finding. So in recent years, there was some criticism of probing. I will present the main concerns about using probes for in interpretability research. So in 2019, Hu and Liang used control tasks. So they randomly generated labels for a text for each of the words, which in distributions were similar to part-of-speech tags, but were randomly assigned to each of tokens, and showed that some probes can also predict those artificial tasks with quite high accuracy. So they pointed out that the important questions in doing any probing experiment is to define control task and measure selectivity. And where selectivity is the difference of accuracy of the probes on control task and real linguistic tasks. So here in part of speech tagging, the linguistic tags will be just assigning part of speech tags, and the random is just generated some random labels for each of the words. So it showed also the drawbacks of applying the probes for part of speech tagging, and I think currently it's considered too easy task for a probe, which is even in a small, very small layer added to the network. This information can be easily memorized, and therefore we cannot make any reasonable argument whether this information is really encoded in the models, because this information could be as well learned by this small layer added afterwards. We made selectivity analysis for structure probes, so that's why we defined this randomly generated trees. And we saw that structure probes are much less prone to memorizing data. So we defined selectivity as the difference between average results for 6 tasks, so including positional baseline, and probing for those random trees. And results for random trees were much lower, so therefore we obtained quite high selectivity. This axis, the y-axis, starts for 0.65, so therefore we could get about 0.2 Spearman correlations for dependency for randomly generated trees, while for dependency trees we got about 0.85. And also what's important to note here is that adding this orthogonal constraint can somehow regularize the probes. So when we add our approach to structured probes, the selectivity rises. Oh, sorry, I skipped one slide. The other concern was whether it's correct to probe for the informations in the model, or we should rather ask which information is useful for the prediction of the model. So in language models, the main task is to predict the masked words. So in BERT, we mask some words. Do you want to predict them? And Eleazar et al. Argued that it's more adequate to really ask what kind of information is used for this task. So when the model can learn some linguistic information only if it needs it for its main task. And they propose amnesic probing, where they identified the parts of the embeddings which encode specific information, for instance, about part-to-speech, and checked the accuracy on masked language modeling when this information was removed for the model. So in this formulation, the probing was a bit reversed. So we really wanted to, when this information is encoded in the model, the accuracy of the main task should be lowered when we remove this kind of information. So this is more, as I would say, more in line also in the definition I provided. So this, we want to explain the causes of the model's prediction. So here we want to identify the kind of information which causes the model to make a right prediction. I think that maybe this approach, this is very good pushback for probing. However, it's also important to remember that we mostly use language models rather not for language modeling now. So we really use them as representation learners. So we are not that much interested how well do they perform on language modeling. We are rather interested whether we can transfer the representations to other language tasks like syntactic parsing or semantic role labeling or even more high-level tasks. So maybe it would be interesting to also to check those amnesic approach when these representations are transferred already to some downstream tasks. So also our current research is on using probes to control the biases, so those unwanted correlations that are learned from the data. And in the beginning, I showed this example when in machine translation, we can translate the English sentence when we use the word doctor, which is male-based biased, and then in translation, we the bias causes us to predict male form in the Spanish, where we need to pick one gender for a noun. And this prediction is often made based on the spurious correlations of connecting this specific profession, doctor, with male gender. And even if in a sentences that uses female pronouns for a doctor, we often default on male gender for this profession. So we think that it's possible also with orthogonal probe or similar approach to separate those type of gender information, where one would be gender bias, for instance, in word doctor and nurse, and the other would be factual gender, which can be gained from personal pronouns like he, him, she, her. And then in translations, we would like to keep this factual gender while removing gender bias. So this is the source information we don't want to keep in those representations to perform the translation well. But on the other hand, we also want to keep factual gender because we want to be consistent about gender in source and target text. So this is actually the work I'm currently working on. So I'm already talking almost for an hour, so maybe I go for a wrap up. I have an additional part of the presentation, but I would say those are just backup slides that I would use if I had more time. I don't know what are our time constraints. Whether I should finish shortly or have some more time.
How many minutes do you need? If it's 10 minutes, then it's still okay, I guess.
Okay. So yeah, maybe like for 10 minutes, I will just go to the closing remarks. I will skip this part. I will also share this presentation, so if anyone is interested, then can ask about this part. So here, I wanted also to talk about a bit different way of interpreting the models, which is not connected with the probes. This is mostly connected with our previous works we made on interpretability. So I will just skip this part. Yeah, so for closing remark, I just wanted to say some few words about my collaborators and my university. I'm at Charles University, which is located in Prague, and so the university is working on applied linguistics for already some time. It was established in 1990s, but the beginnings was in the 60s. There are 20 academic staff, 29 researchers, and 41 PhD students, including me. You have I'd say quite good infrastructure with many CPUs and over 100 GPUs. So at least now there are not many problems with running the even more demanding experiments for our work. So yeah, I want to thank my collaborators, including my supervisor. We worked on the project called LSD, which is an acronym for Linguistic Structures Representations in Deep Networks. So the project's already ended, but we continue our works and look for other opportunities. And many of those works I done with great help and assistance of my supervisor and also other people in the group. So yeah, I wanted to just share the references instead of just one long list of the bullet points with the recent works. I just wanted mostly to share 2 articles and 3 books. So I'd say the most relevant to the study on interpretability. I think those are also good starting points for someone who would like to learn to get like some overview of this field. There was an overview work of Jonathan Belinkov and James Glass, Analysis Methods in Neural Language Processing. There is also the primer Bertology, which is quite popular paper by Anna Rogers, Olga Kovaleva, and Anna Rumszycki. And so yeah, they established also this word Bertology. So they survey a lot of related works which tries to answer how those models like BERT process the language. So yeah, actually probing is only one very specific subfield of this field. There are much more. So just I think there is no primer specifically on probing. So I think it's like very helpful to see a bigger picture, to see some other approaches I didn't have time to describe here. So in NLP there are also 2 books. I think even more, but like here I only focus on 2. So one came as a result of works in our group, Hidden in the Layers. So this was also partial my work with my group, and was also here we describe some of those experiments I mentioned here, and also some other works we've done on interpreting language processing, natural language processing. There is a recent book of Anders Sogard, Explainable Natural Language Processing. I think it came out in last month or December. So there's very up-to-date survey of interpretability methods. Also, there is a more broader approach in book of Christoph Molnar, in interpretable machine learning. So this book is also on other fields than NLP. So if someone wants just to read about interpretability or is not interested specifically in the field of language processing, I would highly recommend this book.